Good afternoon, everybody. Hope you're all doing well on this fine Thursday afternoon. Looking forward to the weekend. Thank you all for attending today. I know your time is valuable. So without further ado, we're going to jump right in. I'm going to hold all questions to the end. At the end of the presentation, I will unmute everybody and we can field the questions at that time. So today we're going to be talking about the comparators and indicators. Specifically, we're going to be talking about the differences between them. For those of you who don't know, who have never worked with me before, my name is Brendan Larcom. I'm one of the product managers here at Mahr Incorporated. I've been working with Mahr for the past 7 years now, and I've been focusing a lot. I've focused a lot during my career on the precision hand tool side of things, which is exactly what we're going to be diving into today. So, topics for today, we're going to go over, obviously, the overall agenda is going to be talking about the differences between comparators and indicators. But to do that, we're going to talk about some background knowledge first. We're going to talk about the differences between measurement versus gauging. Then we're going to look at the differences between dial comparators and dial indicators. And then we're going to go step into the digital comparators versus digital indicators and really get into detail there, because that's where we're seeing a lot of trend moving in the marketplace. Is that we're still seeing that highly accelerated trend of people transitioning from analog equipment to digital, and that is even more so in the digital comparator space. As to exactly why, we'll get to that when we get to those slides. First thing we need to think about when we're talking about what is a comparator versus what is an indicator, we need to think about the fact that there's a major difference between measurement and gauging. Measurement is the process of determining dimension of a part by comparison with an internal standard. Those are usually done by measuring instruments, whereas gauging is the process of determining whether the dimension of a part is smaller or larger compared to an external standard. And those are going to be, again, comparative style instruments or comparative gauges. Anytime when you're comparing an unknown part to a known master or a known artifact, such as a gauge block or a gauge ring, that is by definition what's called a comparative measurement, because you're comparing a known to an unknown. Whereas a non-comparative measurement, sometimes referred to as an absolute measurement, you're not comparing a known to an unknown. You're relying entirely on the accuracy of the internal scale that's built into your measurement device. And so when I say measuring instruments, what am I talking about? Well, measurement instruments always have an internal scale and measure parts compared to that internal scale. So right off the bat, you can think of your hand tools, your scales. All of these types of gauges have the standard built into them. Whereas, as you can see on the screen right now, I have a picture of a caliper. The standard that we're referring to in the caliper is that on the caliper, there's a little rotary encoder that basically just counts rotations, and that's how it's generating measurements. All measurement devices are relatively slow, and they are a higher skill type of measurement. You need to be more of a skilled operator to get an accurate and repeatable measurement, versus a comparative style gauge, which we'll get to comparative styles in a couple slides here. But where measuring instruments lack in accuracy and demand high skill level, they make up for in a wider range of type of applications and dimensions that they can check. And in general, measurement devices usually have a higher uncertainty than gauges. So what do I mean by basic measuring instruments? Well, I got a couple of examples up here on my screen. So for hand tools, you have you have scales, micrometers, and calipers, but measurement instruments also include some larger, more capital type gauges that you may see on the shop floor, such as length machines, laboratory machines, such as the ULM that we have a picture up there. And your height gauges. Your height gauges are all considered measurement gauges. They're not considered comparative gauges. Again, because they're all using their internal scale to make a measurement. Now, when you're talking about gauging instruments, all your gauging instruments are, again, comparative. So when we talk about gauging, Gauging is the process of determining whether the dimension of a part is smaller or larger when compared to an external standard. So again, that external standard here is really what defines a comparative or a gauge based to a measurement device. Comparative instruments, they're always going to be faster and more accurate. They always are going to depend on an external standard, such as a master ring, master disc, or plug, or even gauge blocks. They are going to be faster and more accurate. However, the trade-off is that we have to consider when we're talking about a comparator measurement versus a measuring instrument is a comparator is going to be faster than a standard measuring instrument. It's also going to be more accurate than a measuring instrument. But as a result of that, it is going to be more expensive than a regular measuring instrument. Because again, they're built to that custom task, there's going to have to be more of you're going to have to be able to justify an ROI on some of these comparative gauges. So again, they are going to be a little bit more expensive, but that ROI is usually justified on that increase in cost by that increase in accuracy, performance, and speed. When you're talking about gauging instruments, we typically have 3 different types. We have fixed, variable, and fixed variable. Fixed gauging instrument is something that does not move. It does not change. So when you think of a fixed comparative measurement or a fixed comparative gauge, that's going to be, think of gauging pins, gauging rings, gauging discs. Basically, any kind of a setting standard is a fixed gauge. Go, no-go pins would be an example of a fixed gauge. Fixed gauges, again, are going to be very, very fast in telling you if a part is good or not, but they're not going to give you a lot of information about that part. Yes, they'll tell you if the part is good or bad, but they will not tell you by how much. So it's going to be what it lacks for in terms of data collection and actual measurement, that your measurement data you're getting out of your measurement process is really going to be made up for in speed. So again, fixed gauges are going to be fast, but not a lot of information coming out of that. Then you have something like your variable gauge. So for an example of the variable gauge, I have a 36B IDOD gauge. This 36B IDOD gauge is used for measuring inner and outer diameters. Why it's called a variable gauge is because you can accommodate a wide variety of sizes in there over a large span. Whereas a fixed gauge like a plug, disc, or ring is going to be faster but dedicated to a size. You get a wider variety of sizes that you can measure with a variable gauge versus a fixed gauge. Again, they do require external masters to compare your known to your unknown to make your comparative measurement, but you're going to get a little bit more versatility out of a variable gauge because of that size range that you can measure, and because there's going to be the other benefit that you're going to get is the fact that you'll be able to get actual measurements. You'll be able to see how far off from nominal or how far over tolerance you are, which is very, very important for quality control purposes because it allows quality control engineers to track manufacturing data, to make adjustments, and it also benefits our manufacturing engineers so that way they can make sure if there's any offsets or changes they need to make in the manufacturing process, they can do that. Finally, we have the fixed variable gauge. That's going to be an example of a fixed variable gauge is something like this Dimension bore gauge here. This Dimension bore gauge, you can see we have a bore gauge here. It's made to measure an exact size and a small variation around that size. So a Dimension plug such as this can measure at most plus or minus 100 thousandths of an inch from its nominal size. And that's why we call it a fixed variable gauge. Yes, there's variability in the sizes we can measure because we can measure, again, that plus or minus 100 thou from either side, from nominal, but we are limited to that plus or minus 100 thou range. That is why, again, we're going to be calling a fixed variable gauge because it's going to be, again, made to a dedicated size, but it can measure a small variation within that size. Just like our variable gauge, we can get exact measurements out of our gauge. We can collect those measurements for data collection purposes, and it's also going to be just as fast as fixed variable gauge because they're made to a dedicated size like a fixed gauge. They are going to be just as fast as a fixed gauge. So the fixed variable is really the best of both worlds in terms of that it's going to be just as fast as a fixed gauge, but you can actually get actual measurement results out of it like a variable. So again, gauging instruments fixed. These are made for one dimension. There's no deviations from good or bad. There's no information about the part form. It's going to be the fastest process, and they're always good for one size. While they do have a low initial investment, they are going to be more expensive because you do have to maintain them over the long run. You have to store them, recertify them once a year, and have to make sure that they're kept in good condition. Usually fixed gauges are 2 masters in a fixed gauge. That's going to be your go, no-go, or a min and a max. So again, that's going to be your benefits of your fixed gauge. Moving on, going into detail about the variable gauge again. Variable gauges will indicate how much a part deviates from the standard that it was set to, in this case, a master ring on this 36B gauge. You'll probably get actual deviations, actual measurement information out of it. You can use a fixed variable gauge to find information about the form of the part that you're measuring. You can then use that information to look for trends and diagnose any manufacturing issues. It's fast and easy. It does have a limited measuring range, but they do have a lot of adjustable range. What that means is they can accommodate a wide variety of sizes, but once they're set to a size, they can only measure a small variation around that set size. They are going to be a little bit more expensive, large initial investment, but when they're maintained properly, they can last for decades. So for example, this 36B gauge, there are still examples out there on the shop floor from when they were originally introduced back in the 40s with the original version, and they still work just as well as the day they were made. Variable gauges, again, are always going to require a master to get your comparative style measurement from, so you can compare your known to your unknown. And again, they're going to be fast. You're going to get actual measurements out of it, and they are going to, and you can find out much more information about the part than you can with the fixed gauge. Finally, with your fixed variable gauge, variable gauges are made to a specific size. So again, if we're looking at the example of this Dimentron plug looks to be about a 1/2 inch in size. So most Dimentron plugs at most can have a measurement range of plus or minus 100 thou. So that means this plug right here can measure anything from 600 thou to 400 thou. So that's going to be our total variation in size that can measure. Again, like the variable gauge, you can get actual deviations. They are the least prone to operator influence. And just like the variable gauge, you can learn about the form, and you can find processing trends and use it to diagnose measuring manufacturing issues. They are also going to be fast. Probably they're just as fast as a fixed gauge, and only good for one size. And they are, again, just like the variable gauge, they're a large initial investment. They can usually last for a real long time when properly maintained. So some more examples of gauging instruments. Well, we have some portable options here, such as a snap gauge, an IDOD gauge, or a rail style gauge, like you see here with this 844T. All of your bore gauges, your sweeping style bore gauges, your plug style bore gauges, like the Dimentron we saw in the previous slide, are all going to be examples of gauging instruments. Then we also have bench mounted options of those. So even the high-end gauge block comparators, again, are comparative style instruments because they're comparing master blocks to unknown work blocks. And then you have the same thing for our comparator stands. So in this guy here, this is a ball comparator, and it's set on a setting master and used to measure the diameter of ball bearings to a very exact size. And one of the reasons why it can get so exact and be so accurate is because, again, you're comparing it a known to an unknown. There's a setting master in here, and you're comparing to that unknown size. And again, another example, again, would be the 36B. That covers all of the differences between gauging and measurement devices. So let's talk about the actual comparators themselves, right? Comparators are going to be, an example of comparator would be this Millimetre 1003 that we have a picture of here. An example of an indicator would be this B5M Mahr indicator. In general, the mechanical differences between a comparator and an indicator are going to be very minute. Most indicators use what's called a rack and pinion design, where you have a large steel, you have a solid steel shaft going up and down the length of the indicator with gear teeth on it. And that gear teeth moves a series of gear trains in here, and that produces your measurement. Whereas on the comparator, they use more of a lever-based design. So they have a shorter measuring range when compared to the dial indicator because of that lever style design. Basically what you have inside of here is you'll have a lever with some gear teeth on it. That lever gets actuated by the movement of your contact point going up and down, and that's what generates your measurement. So the real identifying feature for a dial comparator versus a dial indicator is going to be the fact that your dial comparator has much shorter range, but a much finer resolution, a much higher accuracy. Whereas your indicator, something like this, the B5M, is going to be much longer range, have larger resolution, and therefore be less accurate. Before, we are still seeing that rapid changeover from analog to digital in the manufacturing space, particularly as Industry 4.0 comes upon us. So when you're talking about going from an analog indicator or comparator to a digital, what are the advantages? Well, the digital indicator or comparator is always going to provide an exact reading. It's not, there's going to be no guesswork between splitting grads. It's always going to give you an exact measurement. Sometimes some operators can get confused by dial indicators because they can be a little bit tricky to read, particularly when the dial indicator has multiple revolutions built into it. It can be hard to manually track and count all of that in your head, whereas a digital indicator or comparator will just, again, be displaying that measurement. There's no counting you have to do. Compare all digital indicators and comparators can do usually have an auto zero feature built into them, making them faster to set zero. You can also have some ease of life benefits of a digital comparator or an indicator versus an analog, where you can have options for programmable tolerances, presets, units, and dynamic modes where you can measure. So you get a little bit more versatility out of your digital indicator versus an analog. And you can also display much more information immediately to the operator, whether that part is, again, in or out of tolerance. You can show exact sizing using the preset, and you can even, again, change the units if you have to. Obviously, the real main benefit of a digital indicator or a comparator is data output. Again, as we had Industry 4.0 rapidly bearing down upon us, data collection is becoming king. It's going to be the name of the game. And that's why, again, you're really seeing digital indicators and comparators really heavily start to phase out the analog options. What's the differences between a comparator and an indicator? Well, the main difference between the two is going to be the mechanics of it. Like our analog systems, the comparators are going to have typically a shorter range than a digital indicator. They're going to have very, very high resolutions. Some of them can get down to 5 microinches or even sub-micron measurements. Where they really come into benefit, though, is when you have a really high accuracy comparator with a shorter range. They very rapidly approach the performance characteristics that you'd get from a benchtop amplifier at a fraction of the cost. So that is always going to be a big benefit there. But again, the big difference between a comparator versus a digital comparator versus a digital indicator is going to be the internal mechanics of it. Most digital indicators, such as the 1086 you see in this picture right here, use an encoder. So basically what that is you have as the stem goes up and down on an indicator, what you do is on that stem, there's a series of hash marks, and you have what's called an encoder head, and it simply counts the hash marks as they go by. Because it's a very simple technology, you can get longer ranges, but again, they are going to be less accurate, whereas a comparator is going to be more of an LVDT-based design. Comparators, because they're using what's called an LVDT or a linear variable distance transducer, what they're doing is they're always comparing a known to an unknown on their internal standard. So what do I mean by that? Well, in an LVDT, the way an LVDT works is you supply voltage to the LVDT, and then based upon where the rack is in its stroke, how far up your spindle has gone, on the LVDT, that changes the voltage coming out. So what you're doing is comparing voltage coming into the LVDT versus voltage coming out of the LVDT. When you do that, there is a null point, or sometimes called a true spindle position, or a 0 point, where voltage in is equal to voltage out. All measurements on an LVDT style gauge are done in comparison to that point on the scale. So that's why these digital comparators are really more of a comparator in that they are comparing, they're measuring a change. They're comparing to a known standard. In this case, it's going to be that starting voltage, and they're always going to be comparing the unknown output voltage, and that's how they generate a measurement. Your digital comparators, again, very low range, usually about a plus or minus a millimeter or plus or minus 40 thou, but you can get very, very accurate. Because of this, comparative indicators are the perfect match for any variable or fixed variable gauges. So when you have any kind of a application where you need to measure, or you're doing a comparative style measurement, such as on some of these bore gauges or a snap gauge like this, a comparator with its shorter stroke length and higher accuracy is the perfect fit for that. We can even get more accuracy. We can get an example of this is we can put a digital comparator, such as this MillimS 2001W, into a comparator stand. They're ideal for finding deviations from a reference point. They make it very easy to use and read the comparator, so there's very little possibility for error. And if you get a heavy-duty enough stand, you can get the performance of a benchtop amplifier for a fraction of the price. When you're talking about the types of comparators that we have on offer from Mahr, we have a couple of different options here. Start out with our Micro Maxim 2. This is going to be on the less expensive end. It's going to be lower in resolution and accuracy than your other offerings. When we step up from that, we get to the Maxim 3, which is going to be going up in price, but has a little bit more features. And then finally, we have the 2000 series and the 2001 series, which are going to be at the top end of the price range, but because of that, pack the most features built into them. So looking at each one of these three in detail, if we look at the MillimS Micro Maxim, this is a gauge I'm sure many of you have seen on the shop floor. We know this is a comparator because it has that shorter measuring range of plus or minus 1 millimeter. We have selectable resolution, which is something you can't do on an analog or dial comparator. You can see we have a little bit of a tight tolerance, accuracy tolerance here on plus or minus 5 microns. But as you see, when we get forward to the other gauges, that accuracy is only going to increase. Once you get to these Micro Maxims and these other digital gauges, again, you have the option for data interface, where in this case on the Micro Maxim, we can go with the Mitutoyo Digimatic standard. We can communicate through an RS-232 or a USB port. Next up in our offerings, we have the MillimS Maxim 3. Again, these are going to have a little bit shorter measuring ranges, but a little bit bigger, where you can see here, we can either have them in plus or minus 1 millimeter or plus or minus 1.99 millimeters. But as you can see, when you get to that, you see a resulting change in error. So when you have the longer range, plus or minus 2 millimeters, you have 14 microns of error. When you get to the plus or minus 1, you have plus or minus 10 microns of error. What's unique to note, though, when you're talking about digital comparators, and particularly in the accuracy specifications, you'll see here we have a total error limit, and then we have an error limit in a partial measuring range. So what this error limit means is it's going to be the error limit from positive full scale to negative full scale. When you're using a large portion of the measuring range, this is the type of error you expect to see. However, when you're doing a true comparative style measurement, where you're setting this gauge on a master, and you're using only a smaller section of when you're using a much smaller section of the measuring span, you can see your accuracy increases from plus or minus 10 to from plus or minus 10 to plus or minus 1. So again, comparative style measurements are always going to be more accurate, repeatable, and reliable than an absolute style measurement, something that you would take with a caliper, micrometer, or an indicator. Next up, we are going to have our, these are two new gauges from the Mahr, Mahr has on offer, the 2000 and 2001. These are some pretty slick little gauges. Again, you can see they have a tighter measuring range, plus or minus 1 millimeter. But if you go ahead and you take it and you go and look at the error limit, you can see the error limit in this one is given as an equation. This 0.02 in the front, this is called the base accuracy. So this means if you were to, so that means the base accuracy of the movement is 0.02 of a micron. So very, very small. These guys are also going to be very reliable in terms of data interface. Again, you can do USB or Digimatic. We also have options for integrated wireless with the new 2000 and 2001. So you can wirelessly transmit data measurements to a computer directly, no need for a cable. They are also going to be IP64 rated, so great for grinding and honing operations. But what really makes these comparators special is the screen. The Millimesh 2000 and 2001, they have a touch screen based interface. You can see from this picture on the side here, there are no buttons. It is entirely touchscreen based, and that makes it much more resistant to the intrusion of oils and dirts and coolants and all that other sort of nasty stuff that makes precision measurement really hard. They're based on a tried and true technology here at Mahr with our VLDT, very linear differential transducer. Specifically, the Mahr 1301 probe, which Mahr has been making for quite a long time. It's industry tested and trusted. We use the same type of LVDT in a 1301 probe in the new Millimesh 2000, 2001s. And because of that, they're very highly accurate. And they also have a very robust bearing built into there. So this bearing is very, very stiff. And that's what's going to allow you to really get a high amount of repeat out of this gauge is going to be that really good, is that nice rotary stroke bearing that we put in there. That's also going to ensure the longevity of the gauge to make sure that you get those repeatable measurements for years to come. That screen is fully tempered. It's scratch and shock resistant. And we do have options for screen protectors and a case protector, just like your cell phone. Further extend the life of that screen if that is something that is a worry for you. I should also mention that the screen is sensitive enough to be used with anti-cut gloves. So if you have guys on the shop floor wearing their gloves, they will still be able to hit the buttons on the indicator to make it and be able to use it. Again, when we're talking about now, something else that you may have noticed here is this range and error limit table. This is saying if we remember correctly, the Millimesh, its accuracy is given by an equation. So that is deterministic upon how much you move in millimeters on the scale. From our set position, if we move 1 millimeter, we're going to have an accuracy of plus or minus 0.7 of a micron. If we move only 1 micron, our accuracy is going to drop significantly all the way to 0.2 of a micron. Now, moving on, Mahr also has on offer a huge line of indicators. We have our tried and tested 1075 line, fixed size there at 1/2 inch, able to show tolerance. We can lock out functions, IP52 rated. Then we step up to the 1086 and the 1087 line. These guys both have the option for integrated wireless. So again, they can wirelessly transmit measurement data. They have an option of selectable resolutions and come in a variety of different sizes. The 1086 coming out in 1/2 inch all the way up to 4 inch capacities, and the 1087 in 1/2 inch and 1 inch capacities. Then on the topping the line there, we have the HR versions, the high resolution. These are going to have a finer encoder than the standard 1086, 1087, and they will repeat to 1 micron, which is a little bit more tighter than the standard 1086, 1087 line. Again, these guys only come in either a 1/2 inch or 1 inch range. We have to sacrifice the 2 and 4 inch range to get that higher resolution and accuracy. But just like your other indicators, they're going to have programmable references, they can have tolerances, you can lock out functions, do absolute measurements, and they are also, again, IP42 rated. So looking at that at the chart, you can see here at the entry level, we have our 1075 going all the way up to the HRs. And again, very similar to our comparators. What you get more in price is compensated for more in features. When you're talking about digital indicators versus digital comparators, you got to remember both digital indicators and comparators are pretty much useless by themselves. They're usually part of a larger gauging assembly, typically a comparative style gauge. Most digital indicators have half an inch of range. Some have much more, as we saw in the previous slide, where some of them can go out to 4 inches. They come in a variety of ranges and switchable resolutions, allowing them to be more programmable for the exact application that you may have. Indicators are often used in comparative style measurements in a comparative gauge, even though they are not ideal for it. That is often something that you see out on the shop floor or in the real world, where you may not need the resolution and the accuracy of a comparator in your comparative style gauge. So therefore, you can stick with a standard digital indicator. Again, also finally, longer range digital indicators are often used as measuring instruments in bench stands. So they can be used to make length measurements against an anvil. So then that's going to be a true absolute style measurement. So that in this instance, your indicator will be solely functioning as a measurement instrument, not as a gauge. Some examples of some applications for digital indicators. We see them often used in bore gauges, bench style, IDOD gauges, or in stands for absolute style measurements. And these are typical examples of where you see these type of indicators being used. In all these applications, you can also use a digital comparator to again get higher accuracy and at the expense of range. So that's the real rub of this when you come down to it, is that digital comparators and digital indicators for the layman are really two identical devices. What the minutia of the difference is between the encoder versus LVDT style technology really doesn't matter to the layperson. What they're really looking at is that a comparator is a more higher accuracy example of it. Like with most metrology equipment, you trade off that accuracy for a shorter measuring range. So this whole thing really comes down to is that comparators and indicators really are the same thing. One's a measurement device, one's an indicator, but once you get them out on the shop floor, the layperson is only going to really worry about is if it's accurate enough for them. So today we discussed what measurement versus gauging is, and that's how that helps us define what a comparator or an indicator is. We talked about the differences between them, applications for both. We went through some technical data and the Mahr product range and how they fit for ideal gauging instruments and measurement devices. Now, putting on my salesman hat here for a hot minute, why should you go with our products? Why Mahr? Well, we have a wide product range for industrial metrology. We have a team of dedicated specialists for you. Our hand tools with the integrated wireless function will help you reach Industry 4.0 much faster and cheaply. And we often have promotional pricing and high quality to give you guys the best value for your money. At the conclusion of this webinar, a link will be sent to you with a recording. You can also view it on YouTube when it does get loaded up on there. With that, I'd like to thank you for your time. I know it's valuable, and your attention. I hope we learned a lot today. So right now, I'm going to open the microphones up for any questions that people may have. All right, so if you guys want, you should be able to unmute yourselves. Nope. Okay, no questions. All right, well, hey, thank you all for your time and attention. You guys go out and have a great day and an enjoyable weekend. Thank you very much, guys. Have a good day.